2017, Paper 1, Question 4, Sequences and Series. So here we're given the amount of substance remaining in a solution reduces exponentially over time. An experiment measures the percentage of the substance remaining in the solution. And the percentage is measured at the same time each day. And we are given the data over 4 days in the table. So based on the table, what we have to do is estimate in which of the first day is the percentage going to be less than 0.01%. So the fact that we're told that it reduces exponentially over time tells me that this must be a geometric series. So for the geometric series, we can write down our first term, A, is 95, and then we can work out our common ratio. So our common ratio is the second term divided by the first term. So this is day 1 would be term 1, day 2 would be term 2, day 3 is term 3, day 4 is term 4, and what we're looking for is term n. In other words, we want to know on what day will the percentage be less than 0.01%. So therefore we need to find out what is n. So therefore let's look at our common ratio first. So it's going to be 42.75 divided by 95. So we can write that as a fraction, which simplifies to 9 over 20 on our calculators, or you could write it as a decimal. It doesn't make a difference. I'm going to keep it as a fraction just to keep it nice and neat. So what is our general term for a geometric series? Well, if we go to our maths tables, page 20, we can see that geometric general term is T of n is equal to A times or to the power of n minus 1. So what we want to know is when will the term be less than 0.01. So we need to work out what is T of n. Well, it's A, which is 95, times or, which is 9 over 20, to the power of n minus 1. We need to say less than 0.01. So if we need to work out what n is, we can see n is a power. And the only way we can ever work out a power when it's unknown is by getting natural log of both sides. But of course I can't get a natural log of both sides until I have a single term raised to a power on the left and a number on the right. So therefore I must get rid of this coefficient 95 here first. So I'm going to divide both sides across by 95, which gives me 0.01 divided by 95 on the right. And now I can get natural log of both sides. So again, the reason I'm getting natural log of both sides is so that I can apply my log rules and bring down my power of n minus 1. We can see this on page 21 in our maths tables. And again, it's the third rule down here for a log. So if I have log x to the power of q, then I can bring down the q in front of the log. Okay, so if I get natural log of the left, natural log of the right, 0.01 over 95 as a fraction can simplify down to 1 over 9,500. But again, you can keep it as 0.01 over 95. So I'm going to bring down this power, so n minus 1 times natural log of 9 over 20 less than natural log of 1 over 9,500. So I'm going to divide both sides across by natural log of 9 over 20. But we have to be careful here because it's an inequality. So I need to check, is natural log of 9 over 20 a positive or negative number? Because otherwise, if it's negative, it changes the inequality sign. And it is. It's negative. So therefore, that's going to make this become a greater than sign. Okay. So what that gives us then is we want to get n on its own. So I'm going to add 1 to both sides. And note I still haven't found the values of the natural logs on the right. And that's because we don't want to round until the very, very end. The less we round, the better. So we have n is greater than natural log of 1 over 9,500 divided by natural log of 9 over 20 plus 1. So that means that n has to be greater than 12.47. But of course, we're looking for on which day does the substance first going to be less than 0.01. So that means it must happen during the 12th day. So if it's n is greater than 12.47, well, that means that n could be equal to 12.5 or 12.6 or 12.8 or 12.9, which is during the 12th day. So we say the percentage of the substance will be less than 1% or 0.01% during the 12th day. So there was 15 marks going for that, so quite a lot of marks. So we had 5, 8, 12 or 15 for our breakdown marks. So in B we have a square of sides of length 2 centimetres. And we're told the midpoints of these sides are joined to form another square. And this process is continued. And we're given the first 3 squares shown in the diagram. We're told to find the sum of the perimeters of the squares, and we're told that this process continues indefinitely. So in other words, we're looking for the sum to infinity here if we're getting the sum of the perimeters. And we have to make sure that we're giving our answer in the form of a plus b root c centimetres, given that these values are natural numbers. Okay, so let's look at the diagram itself, right? So if we're looking for the perimeter is going to be 4 sides where each side is the length. So in other words, it's going to be 4 times L because it's a square. So it's L plus L plus L plus L. So if we look at the inner square, we can see that if this is the midpoint, that means that these 2 sides must be equal. And if this is 2 centimetres, then this is also equal. So therefore, to find the length of the square side, we can just see that we have a right angle triangle. So if I take out that right angle triangle, we have our midpoint divides the line in half. So that gives me 1 centimetre by 1 centimetre. So therefore, to find the hypotenuse, I can simply use Pythagoras. So h squared is equal to o squared plus a squared. In other words, the hypotenuse is going to be the square root of 1 squared plus 1 squared, which is going to be root 2. So now we know that the length of this triangle is root 2, and root 2, and so on. So now if I want to find the inner square, so the third square, I'll just simply repeat that process. So again, if I do it in blue, the midpoint is going to divide that line in half, which means that when we draw our right angle triangle again, we're going to have root 2 divided in half, so root 2 over 2, root 2 over 2, and h. So again, if I use Pythagoras, we have h squared is equal to o squared plus a squared. So our hypotenuse is going to be the square root of root 2 over 2 to be squared plus root 2 over 2 to be squared, which gives us the square root of a half plus a half, which is obviously just 1. So that means that this rectangle has a side of 1 centimetre and 1 centimetre. So if we look at the pattern then, what we have is the sum of our perimeters of each of these reducing squares in size. Well, the first one is 4 times our width is 2 centimetres, plus the sum of the next one was 4 times the length, which is root 2, and the next one is 4 times 1, and that process continues indefinitely, in other words, to infinity. So we can see that we are multiplying by 4 each time. So we have a common ratio here, and therefore it is a geometric series to infinity. So therefore I can get the sum to infinity formula. So if we write down our first term, well, that's a times 4 times 2, which is 8. Our common ratio is found by getting term 2 divided by term 1. And therefore that gives me 4 root 2 divided by 8, which is root 2 over 2. Sorry, not 4. I think I said 4 a second ago. So our common ratio is root 2 over 2. So therefore, if we look at our sum to infinity, then we can see on page 20, geometric sum to infinity. So in other words, our sum to infinity is a over 1 minus or. And therefore that gives me a, which is 8, divided by 1 minus or, which is 1 over root 2 over 2. And therefore if we sub that into our calculator, we end up with 16 plus 8 root 2 as our sum to infinity. So there was 10 marks going for that, and it was broken down into 0, 5, 8 and 10.